Welcome to the ride.
Welcome back to Babbling On in Babylon. My name is Will, and I'm an aspirant follower of Yeshua HaMashiach. You might know him as Jesus Christ. And this here's the strange little corner of the internet where we delve into the more unusual, crazy, and out there parts of Babylon. And folks, I gotta tell you, I've done a lot of episodes sitting right here in this chair in front of this here computer, talking into this here second-hand microphone. We've talked about mind control, we've talked about monuments, about things hiding in your cell phone and things hiding in your food. And I thought I had a pretty good stomach for all this stuff at this point. I thought I had built up a callus. And then the other day I watched a video that took that callus and just peeled it right back off. So here's where I want to start today. I want to start right where this fella here started in this video, because he earned it. He opens with footage, and if you go looking for it, you'll find it easy enough. It's out there. Footage of a screen, and on that screen, somebody's playing Doom. You remember Doom, right? Classic shooter, run around a maze, blast some demons. It's real simple stuff by today's standards, but let me tell you, I spent a lot of hours of my youth running around in that Doom maze. And that little Marine on the screen, he's a-moving. He's turning corners, he's lining up shots. You remember that? You out there ever played Doom back in the day? Somebody, or something, is playing this game now on the screen, on the video. And then the host says the line that I have not been able to shake since I heard it. He says something along the lines of, imagine being trapped inside that Doom game, a conscious, sentient being, doomed to play Doom over and over and over and over. Sit with that for a second. Because I had to. Because what's actually happening on that screen? And this is not science fiction. This is not a thought experiment. This is a real laboratory in Melbourne, Australia. A company called Cortical Labs. What's happening is that there are 200,000 human brain cells grown in a dish, wired up to a microchip, and those cells are the ones making the decisions. Not a program pretending to be a brain, not an AI, not a simulation of neurons running on silicone. Actual living human neural tissue grown from a real person's real skin cells, sitting there right now, today, playing a 30-year-old video game from my youth over and over and over and over and over again. Now I want to be careful and real honest with you about how I present this, because this is exactly the kind of thing where our little corner of the internet can go two directions, and only one of them is worth our time. One direction is I just start screaming, "The growing brains and jaws! Wake up, sheeple!" And I get you all worked up for 10 minutes, or 20, or an hour. And you feel something, but you don't actually know anything new. Now I'm not gonna do that. I wouldn't do that to y'all. You know that's not how we do it around here. Not here in the little studio. We take the other direction. We sit with the actual, documented, verifiable, published science and we let it be exactly as unsettling as it actually is. Because here's the thing I've learned, babbling on in Babylon for as long as I have. The real stuff doesn't need me to embellish it. It's already right there, at the edge of what a human being can comfortably think about. Trust me. But my job is not to make it scarier. It's already scary enough. My job is just to hand it to you straight and let you feel whatever it is that you're going to feel. All right, let's get into it. So let's build this thing up properly. Let's start with how in the world we got here. Because it did not happen overnight, and it did not happen in secret. It wasn't no conspiracy theory. This has been building out in the open in peer-reviewed journals for the better part of 20 years. Now back in 2008, yeah, way back for some of you folks, but just yesterday for us old folks, some researchers took a sheet of rat neurons, grew them flat, hooked them up to electrodes, and wired the whole business to a little robot. And I'll be daggone if that thing didn't move. The cells fired, the robot rolled. Now, I want you to hold your horses on how impressed you get by that. Because it wasn't nearly as dramatic as it sounds when you say it out loud. It was a flat little grid of cells doing about what a flat little grid of cells does. But it planted a flag. It said, living tissue and machine can actually talk to each other. And from the very start, and I mean from the very first go of this, there was a doubt hanging over the whole enterprise. And it's a doubt that we're going to come back to more than once tonight. So tuck it away back there in your back pocket in the back of your brain. The doubt was this. Is the tissue actually doing something? Or is the machine just taking whatever random static those cells happen to be putting out and dressing it up to look like control? Well, we'll come back to that. Write it down, take notes if you have to. Now then, in 2013, this is a real turning point and it doesn't get talked about near enough outside of biology circles. A Japanese scientist named Shinya Yamanaka, I think that's close, figures out something genuinely wild. He finds that if you take 4 specific proteins and you introduce them to a regular, grown, adult cell, say a cell from your skin, you can reset that cell, roll it back, turn it into what's called a pluripotent stem cell, which is a fancy way of saying a blank cell that can still become almost anything. A liver cell, a muscle cell, a neuron, a brain cell. Now, sit with what that means for just a second. Because it's the hinge the whole rest of this swings on. Before Yamanaka's work, if you wanted human neurons to study, you were in a genuinely dark ethical corner. You needed actual donated brain tissue. And that's about as rare and as heavy a thing as there is. After Yamanaka, all you need is a little skin sample. Any kind of skin. A cheek swab, some blood. Everybody's got some. Yamanaka and a fellow named John Gurdon picked up a Nobel Prize for this, by the way, in 2012. So this isn't fringe science, this isn't some mad scientist in a lab somewhere, or maybe it was. But this is about as mainstream, about as decorated as biology gets. So now you got 2 pieces on the table. You got cells that'll talk to electrodes. And you got a way to make brain cells out of basically anybody's spit. And there's a third piece. And this one's about shape. about geometry, and it matters more than you think. If you grow neurons flat on a dish, they only ever reach out and connect to the neighbors sitting right next to them. It's a real limited little neighborhood. But if you let them grow in 3 dimensions, let them build their cities up and fold in on themselves, the way tissue actually wants to, they start doing something almost eerie. They start organizing themselves. They fold into layers. They start sketching out the rough beginnings of actual brain structure. Kind of the way an embryo does in the womb. Nobody's driving it. It just wants to happen. If you give it room, it just happens on its own. And they call that little ball of tissue that results an organoid. Hold on to that word, because we're going to live inside of it for the rest of the evening. An organoid. So you put all 3 of those pieces together, folks. The electrode talking, the Yamanaka reset trick, and the strange little organoid geometry. And in 2022, Cortical Labs, that same Melbourne outfit, takes about 800,000 neurons, part mouse and part human cells, that old chimera effect, flattens them out onto an electrode array so the chip could actually read them, and they teach it to play Pong. And I want to slow way down here, because teach it to play Pong is doing an enormous amount of work in that sentence. And I don't want you just to blow past it. Sit with that. How do you train something that doesn't have a mouth to feed a treat to? How do you reward a blob of tissue in a petri dish? I mean, you can't pat it on the head. You can't tell it, good job. Well, you could, but it don't have no ears. So here's what they landed on, and it's simple. And if you think about it for more than about 10 seconds, it's also a little bit merciless and dark. Dare I say evil? Neurons, like most living systems, hate chaos. They hate an unpredictable signal. Feed a neuron noise it can't make sense of, and that stresses the system out. You can measure it. So here's the deal Cortical Labs struck with that dish. If you can even call it a deal when only one side understood the terms. Miss the ball, and the cells get hit with scrambled, chaotic electrical noise. Hit the ball back, and the signal goes calm, steady, predictable. Primitive, but effective. Here's the part that ought to stop you in your tracks. Those cells, that organoid, doesn't know what Pong is. Our little friend has no concept of a paddle, a screen, a score, winning, losing, none of it. So technically, the little organoids aren't trying to win a game. As best as anybody can tell, all they are doing, all they ever have been doing, is trying to make the chaos stop. That almost sounds familiar, doesn't it, folks? And this wasn't some wild guess on the researchers' part, not some lucky stumble. They built it around an actual theory out of neuroscience called the free energy principle. And I'm going to give you the folksy version because the technical version will put you to sleep. It daggone near did me just doing the research. But here's what I got out of it. The ideal is that every living thing, from the simplest cell on up to you and me sitting here right now, is constantly, every second, trying to keep its world predictable, trying to avoid surprise. Because out in the wild, a surprise usually means something's gone wrong. A threat showed up. An expectation broke. Something's about to hurt you. Or worse, eat you. So minimizing surprise, keeping things steady and known, that's not some clever training trick the scientists bolted together onto these cells. There's a real argument in the neuroscience literature that this is about the most basic, most fundamental thing a living system does. I reckon that's just common sense. Before thought, before anything we'd recognize as a mind, just reach for the steady, safe state. Reach for calm. Avoid the chaos. Well, if you look back at Genesis, the whole story is about the uncreated creator of all creation coming here to the world that was tohu avohu, chaos, wilderness, unpredictable, and setting it straight, bringing calm to the chaos. Like Yeshua on the boat, calming the storm. Sit with that for a second. That drive, reach for calm, avoid chaos, might be the closest thing to a want that a single cell has. And we're about to build a whole industry around poking at it. And I'll tell you honestly, folks, this is the part of the research that got its hooks in me the deepest, more than the Doom footage even. Because when I first read about the free energy principle, my mind went somewhere real personal, real fast. I thought about anxiety. I thought about what it feels like in my own chest when something in my life goes unpredictable on me. A diagnosis I wasn't expecting, a call I didn't see coming, the ground just shifting under my feet without warning. You know that feeling, that reaching for solid ground, for something steady to hold on to in life. Some very serious people in neuroscience are telling us that might not be a uniquely human thing we layer on top of being alive. It might be a whole lot closer to the actual definition of being alive in the first place. Every living thing, maybe clear down to the cellular level, spending its whole existence just trying to keep the world from surprising it, from going into entropy, from reverting into chaos. Now, here's the catch, and it's an important one because it tells you exactly how far we are and are not from the thing that's going to keep you up tonight. We can grow tissue in 3 dimensions, that beautiful, organized, almost brain-shaped organoid friend of ours. And separately, we can wire up flat tissue to read its signals. What we cannot do yet, not yet, I want to stress that phrase real hard, not yet, is both at the same time. The electrode arrays that read these signals are flat grids. You set a round, 3-dimensional organoid down on a flat grid, you're only ever touching the very bottom layer of the cells. The rest of it, the depth, the real structure, might as well not exist as far as that chip's concerned. It'd be like taking your brain out of your cranium and throwing it down on a motherboard. So for old dish brain, you know, that original ping pong playing setup, they had to flatten the tissue out. Give up the real architecture, the real shape a brain wants to grow into, just so the machine could listen to it at all. Which means, and I want you to really sit with this, folks, what we are looking at right now, today, is the crude version, playing Pong. It's half the design at best. The part of this that would genuinely worry me most, the fully 3-dimensional, properly organized tissue actually talking to a machine in real time, that piece is still missing, but it's still being worked on right now as you're listening to me. Which brings us up to the news that got that video made. and got me sitting in this chair, babbling into this secondhand microphone to you tonight. Cortical Labs took the next step. They call it CL1, and it plays Doom. Not just Pong, but Doom. Have you ever played Doom? It's quite a complicated game. This one's grown from about 200,000 human neurons, smaller than the original dish brain setup. But here's what's the difference. These came straight from skin cells, run through that Yamanaka reset, turned into neurons, and spread across a bed of electrodes. Same deal as before. Do well, stay calm, take damage, die, get flooded with chaos. And within about a week, 1 week folks, it had picked up the basics: moving, aiming, and shooting. That's complicated. And I told myself going into this episode that I was going to stay measured. That I wasn't going to let this show turn into me just reacting. But I'm not going to sit here and pretend I watched that footage with a straight face. And I don't think you should either. It is remarkable. It is genuine, real, documented scientific achievement. And it also turns my stomach just a bit. And I've come to believe both of those reactions are correct at the same time. Because that thing, sitting in a lab running on donated cells reprogrammed into human brain neurons, that computer is made out of a piece of an actual human being, folks. A person who is, as best as I can tell, still walking around out there somewhere, completely unaware that a piece of their own biology is, at this very moment, learning to dodge a pixelated demon in a programmed hallway. Cortical Labs isn't some garage operation either. I want to be fair about that. This is a company that's been at this since 2019. They've raised real money doing it. They've got a defined product line now. You can actually buy one of these units for around $35,000. Or if that's a little rich for your blood, you can rent time on one through what they call, and I promise you I'm not making this name up, Wetware as a Service. $300 a week to log in and run your own experiments on somebody else's living brain neurons. Sit with that phrase for a second. Wetware. Like it's just another category of hardware sitting on a shelf next to your router and your laptop charger. Now here's where my mind goes, folks. I keep imagining what it would actually be like to be the thing in there. Not smart enough, maybe, to know it's in there in any way we would recognize, but something, some flicker of consciousness, cognitive being, stuck playing the same little slice of a decades-old video game. Forever, with no memory of anything before it, no concept that a world exists outside of those four walls of the level. For whatever that tissue is, our little organoid friend, if it's anything at all, there is no before. There is no outside. There's just the game. Over and over. We spent decades, as a species, scared of the opposite thing. Talking about chips in the brain, machines crawling up into us. You know, the whole man becomes machine nightmare. That's classic science fiction. That's the stuff of 100 movies. Almost nobody, and I mean almost nobody, was sitting around worried about it running the other direction. Machine becomes a little bit of man. But that, near as I can tell, watching this unfold in real, published, peer-reviewed science, that's what's actually happening right now in a lab for the price of what a nice used car would run you in some parts of the world. Crazy. Now, I promised you facts first, and I'm going to keep that promise, even when it means taking a little wind out of my own sails. Because that's what we do here, babbling on in Babylon. So let's be fair about something. When Cortical Labs first published that original Pong research back in 2022, the title of the paper used a heavy word. It said the neurons displayed something like sentience. And I want to be careful here because sentience to you and me means somebody's home. Somebody's having an experience. But the way the scientists used the term in that paper was in a real narrow, technical sense. They were pointing at a specific measurable property, not claiming they'd built a conscious mind in a ditch. Didn't matter. The story blew up everywhere, and a good chunk of the neuroscience community got legitimately angry about it. About 30 scientists signed on to a formal published rebuttal. This ran in the same journal, Neuron, arguing the company had reached for a word that oversold what the data actually showed, whether that reach was on purpose to grab headlines or just careless. And their worry wasn't just about scientific accuracy for its own sake, though that mattered plenty to them. The worry was practical. Hype breeds backlash, and backlash, enough of it, could choke off funding and public trust for a whole young field before it ever gets the chance to do the good it might actually be capable of. And that good is real, folks. I don't want to skip past that. This same underlying research, growing living human neural tissue outside a body, lets scientists build actual living models of human disease. Watch a disorder develop in real human tissue in real time, instead of guessing from a mouse whose brain works pretty differently from ours. Test new drugs on something a whole lot closer to a real human system before it ever gets near an actual patient. That could save lives. That could replace a genuine mountain of animal testing that a lot of us already have real discomfort with. It would be a shame, a real shame, if a marketing stunt with a video game dragged all that serious, careful work down with it in the public's mind. Because make no mistake, Doom was a stunt, at least in part. Audience asked for it, and it made for spectacular footage. It got this very here podcast episode made, right? I'm not going to pretend I am above that pool myself. But it drags us right back to the doubt that I told you to tuck away, clear back from 2008. Is the tissue actually driving here? Or is the computer just cleaning up random static and making it look like there's somebody home? And here's where it gets genuinely interesting, because for the first time in about 20 years, we can actually check. The developer behind that Doom demo put the code out in the open. Anybody can go read it, nothing hidden. And what's actually in there is not, as it turns out, just a brain in a box. There's 3 working pieces. First, an ordinary computer chip running conventional AI that's watching the game unfold on the screen and deciding moment to moment when to send a reward signal and when to send a punishment. Second, the 200,000 human neurons themselves. And third, sitting right in the middle, a translator passing messages back and forth between the two. And here's the part that ought to make you sit up. By that developer's own accounting, the overwhelming majority of the actual intelligence at work, reading the screen, running the learning process, telling a win from a loss, that's the ordinary silicon chip, not the cells. He was worried enough about this that he ran an actual test to check it, pulled the living cells clean out and replaced them with pure structureless random noise. And the learning stopped dead. So the tissue is doing something real. It's not just theater, not just a marketing prop sitting in a fancy glass box for the cameras. But it's a smaller piece of the picture than the headlines let on. The honest read, best as anybody outside the lab can tell you today, sits somewhere in the middle. This is not a brain playing a video game on its own, and it's not nothing either. So that's where things stand today, near as the public record shows us. And here's where I think it's headed. And this is the piece I want to leave you with going into the break, because it's going to set up everything we get into for the rest of this show. I don't believe that small biological piece of the puzzle stays small. Labs all over the world, and I mean all over, this is not confined to one company in one country, are racing right now to solve that flat versus three-dimensional problem I told you about earlier. Racing to grow this tissue properly, in its real shape, and get it talking to a machine without having to flatten it out and throw away most of what makes it interesting in the first place. And it is already, right now, turning into a real business. Not a research curiosity, a business with a price list. There's a company out of Switzerland, Final Spark, and their whole pitch runs on renting out access to living human neural tissue over the internet. You pay a monthly fee, you log in from wherever you happen to be sitting, and you run experiments on 16 tiny human mini brains that they're keeping alive right now in a lab on your behalf. And their whole sales pitch runs on the same hook this entire episode is running on. Power. Energy. They claim these living systems can run on up to 1 million times less electricity than a conventional chip doing comparable work. So what started as one strange, one-off experiment in a lab is fixing to become a subscription service. And I believe, and I want you to be clear, this next part is me looking down the road rather than reading you a headline. But I believe sooner rather than later, somebody closes that last gap. Somebody gets a full, properly three-dimensional organoid talking to a machine the way it was actually built to talk. Not flattened out and hobbled to fit an electrode grid, but a brain, an organoid. Now, I know what some of you are thinking, because I thought it too. Most of the smarts, by that developer's own admission, are sitting in the conventional chip, not the living tissue. The cells are doing a small piece of the work. So maybe it'd be easy to hear all this and just wave it off. Nothing to see here, mostly silicon anyway. But folks, I want you to sit with this next thought all the way through the break, because it's the thesis, the central subject of this whole episode, and everything else we talk about tonight builds off of it. Being smart was never the scary part of the story. It never was. Being smart and being awake, those are two completely different things. You can be extraordinarily good at solving a problem and still, as best as anybody can tell, feel absolutely nothing while you do it. A calculator's good at math, but nobody worries that a calculator is suffering. So the real question hanging over everything we're going to talk about for the rest of this episode isn't whether that tissue is clever or smart. It's whether anybody, in even the faintest, most primitive sense of that word, is actually in there. And I want to leave you with one more image before we hit the break, because it's the one that's been sitting with me the longest out of everything in that video. Picture the most basic version of awareness you can imagine. Not thought, not language, not even really a self the way you or I would recognize one. Just a flicker, a leaning towards, wanting things to be calm instead of chaotic. If that flicker exists anywhere in that dish, even if it's just a self-awareness of a dull fish, and I want to stress nobody credible is claiming that it does. Not yet. Not with any confidence. But if it does, then what we've built is a loop. A closed little loop with no doorway out of it. Chaos, calm, forever, world without end. And never once a glimpse of a sky, a face, a memory, anything at all outside of those four walls, a 30-year-old video game level. And chaos, calm, forever. We don't know if that's happening. I want to be crystal clear with you because I will not be the guy who tells you it definitely is just to keep you listening. We don't know. Nobody knows. And that's not me just being coy. That's the actual, honest, current state of the science. And we're going to dig into exactly why nobody knows and why it might be a whole lot harder to ever find out than you would think right after this break. Because it turns out the question of who's in there has a much stranger history than just this one Melbourne lab. And it reaches into some genuinely unsettling territory about how much we actually understand about consciousness in general, including, folks, in living, breathing human beings we've had lying right in front of us in hospital beds for years without knowing they could hear every word that we said. Stick around, folks. Grab you some refreshments. Might even grab you a snack or two. Definitely keep your Bibles handy. We'll be right back after this.
Babbling on in Babylon, the stories keep rolling, the beat goes on. From shadows deep to the break of dawn, we keep babbling, babbling on. Flip the page, ancient words on the mic, conspiracies keep rolling, the beat goes on. From shadows deep to the break of dawn, we keep babbling, babbling on. Flip the page, ancient words on the mic, conspiracies, prophecies ride through the night. From heart to the heavens, the signs in the sky, asking the questions they don't want you to try. Truth ain't clean, it's a puzzle and a fight, but we crack it wide open when the time is right. Whispers in the dark, voices in the dawn. Welcome to the chaos, Babylon storm. Babbling on in Babylon, the stories keep rolling, the beat goes on. From shadows deep to the break of dawn, we keep babbling, babbling on.
Alrighty, welcome back to Babbling On in Babylon. Before the break, we left off with a question I want to put right back in front of you, because it's the spine of this whole episode. Is anybody home in there? Not, is it smart? We settled that one already. A regular old silicon chip is doing most of the heavy lifting, even in that Doom demo, remember? Smart, we got plenty of. The question that actually matters, the one that ought to keep you up, same as it kept me up, is whether there's some flicker of actual experience happening inside that dish. And I told you at the end of the last segment that finding out might be a whole lot harder than you'd expect. So let's get into why. Now I'll tell you, I spent a couple of nights this week just sitting with my Bible on my lap in front of this old busted PC. Not really reading either one, just turning this question over. Because it's a strange spot to find yourself in as a person of faith, digging into this kind of material. Part of me wants to just wave it off. It's a dish of cells. It's not a person. Don't ever think it. And another part of me can't quite let it go that easy. Because if there's even a sliver of a chance that something in there is capable of experiencing anything at all, then waving it off starts to feel like exactly the kind of carelessness Scripture warns us against when it comes to how we treat life, in any form it takes. We'll get all the way into that side of it, eventually. But for now, I want to give you the actual scientific case for why this question is so much harder to answer than you'd think when you first walked in. There's a neuroscientist, a real respected fella, not a fringe character. This is mainstream academic neuroscience we're talking about. Name of Mark Solms. And Solms has spent a good chunk of his career arguing something that runs almost exactly backwards from what most of us were taught in school, if we were taught anything about this at all. We tend to picture it like a ladder, right? Way down deep at the bottom, you got simple reflexes, the primitive core. Climb on up, you get basic behavior. Keep climbing, you get memory, and then reasoning, and then language, and way up at the very top, after you've built all that other stuff first, somehow, consciousness switches on. Like a light at the top floor that only comes on once the whole building's finished. Solm says that we got it upside down. He argues feeling doesn't sit on top of intelligence, waiting for enough complexity to accumulate before it shows up. He argues it's the foundation everything else gets built on. That it comes straight out of the most basic drive there is, staying alive. Think about what showed up first. I mean, evolutionary speaking, and I'm not talking about Darwinism. It wasn't logic. It wasn't language. Lord knows. The earliest living things on this planet weren't solving equations. They were doing something a whole lot older and a whole lot simpler. Moving towards what kept them alive, moving away from what didn't. And Solm's argument is that something like feeling, some primitive, bare-bones version of this is good for me or this is bad for me, was already present, right there at the most basic level, long before anything we'd recognize as thinking ever showed up on the scene. Now hold that thought right up against what we talked about in the last segment. Chaos when the cells fail, calm when they succeed. That's the free energy principle again. That same drive every living system seems to have. Reaching for the predictable, or running from the surprising. And if Solms is right, and I want to stress this is a real position held by a real scientist, not something I'm cooking up for effect. That drive isn't just sitting next to feeling. It might be where feeling actually comes from, ground zero. Which means, and this is the part that got its hooks all the way into me, maybe we've had the whole picture backwards. Maybe we're not slowly assembling a mind, piece by piece, and waiting for it to wake up once it's sophisticated enough. Maybe we're poking directly at the exact mechanism feeling comes from. Right from the very first moment somebody flips the power switch on that dish. Not building up to it. Starting right in the middle of it. And if that's true, if something in there did start to feel even the burst flicker of it, we would probably miss it completely. And I don't say that to be dramatic, folks. I say it because we've got a documented, real-world, medically verified example of us missing it in an actual human being laying right in front of trained doctors for years. Now let me explain what I mean by that. Back in 2006, a scientist by the name of Adrian Owen was working with a young woman who had been written off, diagnosed vegetative. That's about as final a word as medicine hands out. It means, as far as anybody could tell from the outside, there was just nobody left home. No awareness, no inner life, just a body being kept alive. Owen puts her in a brain scanner, and he asks her, knowing full well she can't respond, can't move, can't speak, to just imagine playing tennis. Picture it, swinging the racket. And her brain lit up. The exact same regions that light up in you or me when we imagine the same thing. Precisely the pattern you'd expect from someone fully awake, fully aware, and completely unable to show it in any other way. She wasn't gone. She'd been in there the whole time. She just had no way, none, of letting anybody know. And this isn't a one-off, isolated miracle case either, which is the part that ought to really trouble you. A later study following up on this same question found that something on the order of 1 in 4 patients diagnosed as vegetative, written off by trained medical professionals doing their honest best, are actually still aware, still in there, just locked behind a body that gives no outward sign of it. So sit with that for a second before we go any farther, because I want you to really feel the weight of it. If we can miss a fully conscious human being, someone with a whole life, a whole history, a family standing at that bedside, lying right there in front of trained doctors with all our scanning technology for years at a stretch, what on God's green earth makes us think we'd catch it in a clump of lab-grown cells the size of a lentil, sitting in a dish, hooked up to a handful of electrodes? And there's a piece of Owen's broader body of work that I think deserves a mention here too, because it shows this isn't a one-time fluke of one clever experimental design. He and other researchers doing this same kind of work have gone on to find similar signs of hidden awareness in a whole range of patients who'd been written off using the same old bedside methods. Methods that basically boil down to, does the patient respond in any way we can visibly see? And over, when they go looking with more sensitive tools, the brain scanners, the careful protocols, they keep finding people who are still in there. Which tells you something uncomfortable about how competent we've historically been as a medical community about a question we know we're getting wrong on a regular basis, right up until somebody built a better way to ask it. And here's what keeps nagging at me about that comparison. And I want to lay it out plain because I think it's the crux of the whole thing. That young woman had a fully formed adult human brain. Decades of memory, language, relationship, a whole life already lived, sitting right there behind a body that just wouldn't cooperate anymore. Doctors had every reason in the world to expect a person might still be present, and they still missed it for years, until somebody thought to ask the right question in the right way. Now compare that to a clump of neurons that never had a body, or organoid. It never had a childhood, never had a single day of ordinary life to build itself out of. If awareness is hiding in there at all, it wouldn't look anything like we know to check for in a hospital bed. it'd be something stranger. Something with no history and no context to help us recognize it. Even if we happen to be looking dead at it, we'd have even less of a fighting chance than those doctors did. And they missed a grown woman with a whole life behind her eyes. There's a philosopher, David Chalmers, who gave a name to exactly this puzzle. And it's called, and I think this is about as honest a piece of terminology as you'll find anywhere in academia, the hard problem of consciousness. And here's what it says, plain as I can put it. We could, theoretically, map every single cell in a brain, every connection, every signal, the whole wiring diagram down to the last synapse. And we would still have no earthly idea how any of that turns into an actual felt experience. How electrical noise becomes the color red. How it becomes the sting of a burn or the ache of a missing somebody. Knowing the wiring diagram completely does not, by itself, get you 1 inch closer to knowing whether the lights are on inside. And it gets stranger still, because we like to comfort ourselves with the ideal that feeling requires a certain specific part. Like pain receptors, particular brain structures we can point to on a diagram and say, there, that's the part that does it. But even that comfort is shakier than you would think. Insects don't have anything like a visual cortex, the part of our brain we'd normally point to and say, that's what makes seeing possible. And insects, by any reasonable measure, clearly see. They navigate, they respond to light and shadow and movement in ways that sure look like seeing from the outside. So whatever's doing the seeing work in a bug, it isn't built anything like ours. Which tells you feeling, if it shows up in these systems at all, might not run on the parts we'd think they'd go looking for. It might run on architecture we wouldn't even know to check. Now I gotta be honest with y'all, this is where I went and did some reading past what the original video covered. Because I wanted to understand the full shape of this debate before I brought it to you. And I found there's actually a whole philosophical tradition wrestling with exactly this puzzle. And one piece of it in particular I think you need in your back pocket. Philosophers have this thought experiment they call a philosophical zombie. Not the shambling, brain-eating kind, don't worry. This is a hypothetical being that looks exactly like you, acts exactly like you, responds to a hot stove the same way you would, says ouch the same way you would. But there's nobody home. No inner experience whatsoever. All behavior, zero feeling. And the whole point of that thought experiment, going clear back decades before anybody was growing neurons in a petri dish, is to ask a question that turns out to be a lot harder than it sounds. Could such a thing exist? And if it could, if you genuinely cannot rule it out, then behavior alone, no matter how convincing, no matter how sophisticated, can never actually prove to you that somebody's really in there. Do you see where I'm going with this? That thought experiment was cooked up in an armchair, purely hypothetical, as a way of probing the edges of what we can and can't know about other minds. And now, folks, we've built the actual laboratory version of it. A system that responds to stimulus, that adapts, that learns to avoid a bad signal and reach for the good one. All the outward behavior a feeling creature would show. And the philosopher's own thought experiment tells us, straight up, that behavior like that is not, and never can be, sufficient proof of anybody actually being home. And here's the detail from that original research that I genuinely can't shake, and I want to lay it out for you plain and simple. Well, as simple as I can. When the electrical noise fed into these cell cultures get too loud, too chaotic, the tissue turns its own response down, dampens it, almost like it's trying to block the noise out, the way you or I might squint against a bright light, or cover our ears against a siren. Now, something in genuine pain would do exactly that. Turn away, dampen the response, try to make it stop. But so would something that feels absolutely nothing at all. A purely mechanical system, no experience whatsoever, could show the exact same dampening behavior as a straightforward engineering response to an overloaded input. Nothing more meaningful than a circuit breaker tripping. Backing away from a bad signal is not, by itself, the same thing as suffering. And here's the part that ought to really sit with you. From the outside, looking only at the behavior, there is no test. None. Not one, not currently. They can tell those two possibilities apart. A system in genuine distress and a system doing nothing but obeying its wiring would look, from where we're standing, exactly identical. Now, I told you back in segment 1 that when Cortical Labs first published that Pong research in 2022, they used the word sentience in the title, and that set off a real fight inside the neuroscience community. Now I want to go a little deeper into that fight, because it directly connects to everything we just walked through, and it tells you something important about how seriously, or how carelessly, this whole field is handling the question we've just spent 20 minutes on. About 30 scientists put their names on a formal, published rebuttal in that same journal, arguing the term had been stretched well past what the actual data could support. And that fight has not cooled down, folks. If anything, it's heated back up, and recently. This past November, in 2025, so we're talking a matter of a year ago, less, as I sit here recording this, a group of the field's own leading researchers gathered at a conference to hash this out directly. And I want you to hear how some of these folks, people who've built their entire careers on this exact research, are talking about their own field right now. One of the organizers, a researcher out of Stanford named Sergiu Pasca, put it about as plain as you could ask for. He said using accurate terms that neither hype nor misrepresent the work really matters, because overly expansive claims risk confusing the public and the policymakers who will eventually have to decide how or whether to regulate any of this. Another researcher out of Cold Spring Harbor went further still, called the whole push to build organoid systems that rival silicon AI a scientific dead end. Now sit with that. These are not outside critics. These are not folks with a grudge against technology. These are people who've dedicated their working lives to exactly this research, standing up in front of their own colleagues and saying, "Slow down. What's your language? You're going to bring a hammer down on all of us if you keep letting the marketing get ahead of the science." And part of what those researchers were wrestling with at that gathering is something I think is worth handing you directly, because it clears up a confusion I had myself going into this research. There's actually a real hierarchy scientists use here. And these three words, intelligence, sentience, consciousness, do not mean the same thing, even though we throw them around like they're interchangeable in everyday conversation. Intelligence, in the way most researchers use the term, just means the ability to solve a problem, to adapt, to organize towards some kind of goal. By that measure, Honeybees have intelligence. Ants have intelligence. Pretty much anything with the ability to navigate its environment and solve puzzle counts. That's a relatively low bar. And as near as I can tell, nobody seriously disputes that a dish of neurons chasing calm and avoiding chaos clears that bar. Sentience and consciousness sit further up that ladder, and they're a whole different animal. The capacity to actually feel something, to have a subjective experience happening on the inside, not just behave in a way that solves a problem from the outside. And that's exactly the distinction the scientists at the gathering were trying to protect. Because when a company reaches for a word like organoid intelligence, or worse, sentience, in a press release, most regular folks hearing it, you and me sitting at home, we don't parse that fine distinction. We hear there's something in there that can feel, when what the data might actually support is nothing more than there's something in there that can solve a very simple problem. Those are two wildly different claims, and conflating them, whether on purpose to sell headlines or just by careless wording, is exactly the kind of thing that got 30 scientists angry enough to put their names on a public rebuttal. And even the field's own founding figures don't agree with each other on the timeline here, which tells you plenty about how unsettled the ground actually is. One of the researchers most responsible for framing this whole area, a fellow named Thomas Hartung out of Johns Hopkins, he's the one who coined the term organoid intelligence in the first place, has said publicly that a system that actually learns the way these companies are promising might take years and years of training, not unlike how a human being learns, which puts a real dampener on any near-term promises. Meanwhile, over at Final Spark, that Swiss company we talked about, one of their co-founders has said he believes these systems will be way more useful than quantum computers today, within about 10 years. Years of caution on one end, a decade to outshining quantum computing on the other. Same underlying field, same underlying cells. That's not a field that's got this figured out, folks. That's a field still arguing with itself about basic terminology, in public, in real time, while simultaneously selling the product. Now I want to bring Final Spark back into this conversation properly, because I mentioned him at the end of segment 1, and I don't think I did justice to just how far their approach actually goes, and it bears directly on this whole "is anybody home" question. Where Cortical Labs works with flattened neuron cultures, Final Spark works with actual three-dimensional organoids. You remember our little friend, the organoid. Proper little clusters of tissue, roughly 10,000 neurons each, closer to that real brain-like architecture we talked about needing in segment 1. And their training method goes a step further than chaos and calm. They use reward chemistry directly. Actual dopamine. The same chemical your own brain releases when something good happens to you. Food, a win, a hug from somebody you love, encapsulated in what they call a molecular cage. It's invisible to the tissue sitting there dormant until the researchers decide the organoids earned it. Then they expose it to a specific frequency of light, which breaks that cage open, and the dopamine floods in as the reward. Now, I want you to notice something about the language I just used, folks, because I chose it on purpose, and I want to be transparent with you about that. Earned it. Reward. I'm using words we normally reserve for creatures we already agree can want things. And that's exactly the trap this whole field keeps stumbling into and getting called out for. The words we reach for naturally, the words that come easiest to a human mouth describing this stuff, are the exact same words that imply somebody's home. We can't even talk about this technology accurately without our language quietly assuming the very thing nobody has actually proven yet. And here's the thing that really sits heavy with me about that dopamine cage setup in particular, more than the chaos and calm training we talked about last segment. Chaos and calm, you could almost squint and call that a form of information. Noisy signal, clean signal. That's at least in the neighborhood of ordinary computing. But dopamine is not information. Dopamine is the actual chemistry of pleasure. It's the same molecule at work whether you're talking about a mother's love for her newborn or a man's addiction tearing his life apart. Researchers are quite literally locking a pleasure chemical in a molecular cage and releasing it into a living human tissue on a schedule of their choosing to shape behavior towards an outcome they've decided on. Now, I want to be fair. Biomedical researchers use reward and reinforcement techniques on animal tissue all the time. This isn't some brand new moral territory in the broadest sense. But we are talking about human neurons here, grown from a real donor's real cells. And I don't think it's unreasonable to ask out loud, right here, who decided that was theirs to do? And did the person those cells came from have any earthly ideal when they agreed to donate a bit of skin or blood for the research, that research would eventually mean this? Hold on to that question, folks. Write it on a sticky note if you have to. Because that exact question, who decided, and did anybody actually agree to it, is going to be the central subject later on. But before we can get there properly, I think you need to understand something else first, because it changes the whole flavor of that constant question once you know it. And that's who's actually paying for a huge amount of this research in the first place. So here's where we land for this segment. And I want to say it plain because I promise you facts first, and I intend to keep that promise even here, especially here. We do not know if anybody's home in these dishes. Nobody credible is claiming certainty in either direction. And anybody who tells you different, either definitely conscious, this is monstrous, or definitely not, quit worrying, is selling you something past what the actual science can support. Now, I want to be real honest with you, too, about where I personally land on all of this, for whatever that's worth to you, and I'll get into the deeper why of it later on. I don't think the honest answer is, don't worry about it. I also don't think the honest answer is, panic. I think the honest answer, the one that actually respects both the science and the seriousness of the question, is something closer to reverence. A kind of careful, watchful humility in the face of something we plainly do not understand well enough yet to be moving as fast as we're moving. And that word, reverence, is not a word you hear much in the press releases coming out of these companies. You hear efficiency, you hear breakthrough, you hear scalable. You don't hear reverence. And I think that gap right there between the language of industry and the seriousness of the actual question tells you something important all on its own. But here's what unsettles me most sitting with all this. if we genuinely don't know, if the best neuroscientists and philosophers working on this today will tell you, honestly, under their own names in published journals, that there is currently no test that can settle the question, you would think, wouldn't you, that everybody involved would be moving about as slow and as careful, as transparent as human beings know how to move. Ethics boards on every project, full public accounting of every dollar. Real caution. Well, folks, I went and followed the money on this, and I think you're going to want to sit down for this next segment, because it turns out a whole lot of the money behind this research isn't coming from university grants chasing pure curiosity. It's coming from some of the most powerful, most secretive institutions this country's got. And once you see who's actually writing the checks and why, I think that "is anybody home?" question we just spent 20 minutes on is going to hit you a whole lot different. I don't know about you, but I need to refresh my refreshments and wet my whistle. Stick around, folks. We'll be right back after this.
Well, you know what time it is. Every old country gathering had that moment. The basket made its way down the aisle. It's how the lights stayed on and the doors stayed open. These days, it looks a little different. If this video brought you any value, follow over on Rumble. Share it with someone who might need it. If you want to support directly, there's PayPal for a one-time gift, Ko-Fi for a few extras, and Patreon for the deeper content that doesn't always fit neatly here. And if all you can do is share it, that matters more than you think. Thank you. Truly. Alright, back to the show.
Welcome back, welcome back, welcome back. Y'all refreshed? Alright, get comfortable, pull in close. Where'd we leave off at? Oh yeah, we was talking about if we genuinely don't know whether anybody's home in these little petri dishes filled with neurons and computer circuitry, you think everybody involved would be moving slow, careful, keeping things transparent. Well, folks, I went and followed the money on this. I spent a good chunk of my research time this past couple of weeks doing exactly that. Not guessing, not speculating, just pulling public records, government contract announcements, press releases, and the actual paper trail. And what I found is not hidden. I want to say that right up front, because that matters for how we talk about it. Everything I'm about to lay out for you is sitting in public view, announced with press releases, published on government websites. Nobody snuck this past anybody. But public and widely known are two very different things. And I'd wager that most folks listening right now, that's you, had no idea how deep this actually runs. Let's start with some basic vocabulary, because you're going to need it for the rest of this segment. Most of you have heard of DARPA, D-A-R-P-A. That's the Defense Advanced Research Projects Agency. Anybody that's been down rabbit holes with me are well aware who DARPA is. The Pentagon's outfit for dreaming up tomorrow's technology today. Been around since the late 50s. They're the ones credited with early work that eventually became the internet, among 100 other things. What fewer folks know about is DARPA's quieter cousin over on the intelligence side of the house. It's called IARPA, the Intelligence Advanced Research Projects Activity. And IARPA doesn't sit inside the Pentagon. It sits inside the Office of the Director of National Intelligence. That's the umbrella that sits over the whole intelligence community. CIA, NSA, all 17 odd agencies under that tent. IARPA is, in plain terms, the intelligence community's own version of DARPA. Same basic mission, fund the wild, speculative, high-risk research that might give the country an edge a decade down the road. Just aimed at intelligence problems instead of battlefield ones. Now I want you to hold both of those names in your head, DARPA and IARPA, because both of them show up later in this story. And they show up for a reason that, once you hear it, is going to feel obvious in hindsight. And I want to be upfront with you folks about something before we go any further, because I think it changes how you should hear everything that follows. Neither one of these agencies does the actual research themselves, generally speaking. They're not laboratories full of government scientists in white coats. They're funding bodies, program managers with a budget and a mission, going out and finding university labs, private companies, research consortiums, and cutting them a check to chase a specific hard problem. Which means every dollar figure I'm about to give you traces straight back to an actual named institution doing actual named work, not some faceless government project hidden behind a wall. That's part of why this is so easy to document, once you know where to look. Here's the thing that connects almost everything we're about to walk through, and it's not some hidden conspiracy. It's a problem these agencies state right out loud in their own public documents. Data storage. Plain old data storage. Think about the scale of what the intelligence community is sitting on. Surveillance feeds, signals intelligence, reconnaissance. Decades of it, growing every single day, and growing faster all the time. And storing all of that, the conventional way, on server farms and tape drives and hard disk, that is genuinely, physically, financially enormous. IARPA's own public materials put it plainly, and I'm going to read this close to how they said it because I don't want to put words in their mouth. Today's exabyte-scale data centers, that's 1 followed by 18 zeros worth of bytes, occupy huge warehouses, burn through megawatts of power, and cost hundreds of millions of dollars just to build, let alone run year after year. So back in 2018, 2019, IARPA launched a program with a name that sounds almost boring on purpose. The Molecular Information Storage Program, MIST for short. And the goal, stated plainly by their own program manager, was, quote, a data storage moonshot. To shrink an exabyte-scale data warehouse down to a tabletop, with the operating costs shrinking right along with it. And how do you do that? DNA. Actual, literal DNA. The same molecule that carries the genetic code in every living thing on this planet. Repurposed as a storage medium for digital information. And I want to give you a sense of why anybody would even think to try this. Because the numbers are almost hard to believe. DNA can theoretically pack something on the order of tens of millions of gigabytes into a single gram of material. Properly stored, it can last not decades, but centuries, maybe longer. without degrading. We're talking storage density and durability that makes every hard drive humanity's ever built look like a child's toy. So IARPA put real money behind two competing teams to chase this. One team, up to $23 million, led by the Broad Institute of MIT and Harvard, working alongside a French DNA synthesis company and a Harvard research lab. The other team, up to $25 million, led by the Georgia Tech Research Institute, working with Twist Bioscience, the University of Washington, Microsoft, and a company called Roswell Biotechnologies. And here's a detail I think you'll find as telling as I did. The independent testing of both these systems, checking whether the claims actually held up, got farmed out to Los Alamos National Laboratory, Sandia National Laboratories, and the U.S. Army Research Laboratory. That's the nuclear weapons complex, folks. That's who's checking the homework on the DNA data storage project. Now here's where this stops being a history lesson and starts being current events. That Georgia Tech and Twist Bioscience research, the DNA storage side of the program, that work didn't just sit in a government report gathering dust. It became a real company. Back in May of this past year, 2025, Twist Bioscience spun off its entire DNA data storage division into a brand new, independent company called Atlas Data Storage. And when Atlas went out to raise their initial funding, $155 million for a company that's barely a year old, you know who was sitting at the table? Right alongside Jeff Bezos' personal investment firm and a couple of major venture capital outfits? In-Q-Tel. Now, if that name doesn't ring a bell, let me tell you exactly what it is. Plain and documented. No embellishment needed because the truth of it is strange enough on its own. In-Q-Tel is the Central Intelligence Agency's own venture capital fund. I want to say that slow so it lands. The CIA has a venture capital arm. It's set up as an independent nonprofit. It's sitting on something in the neighborhood of $1 billion in assets, and its entire purpose is to identify promising private sector startups and get the government a foothold in their technology early, long before it's mature enough for a normal government contract. And this isn't some obscure theoretical arrangement either. In-Q-Tel's most famous success story is a company called Keyhole, which they funded back in 2003 to build satellite mapping tools for the Pentagon. Within a couple of years, the commercial version of that same technology launched to the public. You've probably used it. It's called Google Earth. And I want to give you a sense of scale here too, because I don't want you picturing some tiny, obscure operation. By their own accounting, In-Q-Tel makes somewhere in the neighborhood of 50 to 60 investments a year. One of their own executives said in an interview I dug up that 95% of the companies they back have never done a lick of business with the federal government before. Meaning their whole model is finding ordinary commercial startups, private companies just trying to build a product, and showing them a path into government work they never would have had otherwise. Typical checks run $1 to $4 million. Sometimes smaller seed investments on top of that. And this outfit has been doing this since 1999. We're gonna party like it's 1999. It's not new. It's been humming along in the background of Silicon Valley for going on 3 decades, quietly threading intelligence community interest through the commercial tech sector. So the same fund that helped start Google Earth is now sitting on the cap table of a company built directly out of intelligence community funded DNA storage research contracts. That's not a conspiracy theory, folks. That's a matter of public record, announced in press releases, sitting right there for anybody willing to go read it, including you. Go check it out. Don't take my word for it. Fact check me. I dare you. Double dog dare you. Now let's swing back over to DARPA, because they were working a parallel track, and their framing is even more direct about what problem they're actually trying to solve. Back in 2017, 2 years before IARPA's MIST program launched, DARPA opened up its own effort called Molecular Informatics. An official's briefing industry on this program said, plainly, on the record, that the goal was to develop completely new kinds of data storage and processing technology to handle the absolute flood of information coming in from reconnaissance, electric warfare, signals intelligence, and persistent surveillance. Read that list again. Reconnaissance, electronic warfare, signals intelligence, surveillance. This was never dressed up as pure academic curiosity. It was framed, from day one, in the government's own public briefing materials as a solution to a military and intelligence data problem. And this molecular computing thread has a longer history than even that. One that predates the DNA storage stuff by about a decade. And it takes us into the chip side of this whole conversation, not just the DNA side. Back in 2008, DARPA launched a program called SYNAPSE. That's an acronym. Systems of Neuromorphic Adaptive Plastic Scalable Electronics. That's a mouthful, isn't it, folks? And it ran for about 6 years, with somewhere north of $50 million behind it. The goal was building computer chips that mimic the brain's architecture directly into silicon. Not living tissue this time, but circuitry designed to fire and communicate the way that neurons do. That program produced a real working chip called True North, developed by IBM. And it's a genuine engineering marvel. 1 million programmable artificial neurons, over 200 million synapse-like connections, running on a sliver of the power a conventional chip would need. And where did that chip end up? Well, in 2016, Lawrence Livermore National Laboratory, that's one of the crown jewels of America's nuclear weapons research complex, built a True North-based system specifically to support their core missions. And those core missions, stated plainly, are cybersecurity and the stewardship of the United States nuclear weapons stockpile. Now let that one sit with you for just a second. A brain-inspired chip born out of a DARPA program doing work inside America's nuclear weapons program. Makes the hair on the back of my neck stand up, folks. And Synapse didn't just produce one chip and fade away either. It planted the seed for basically the entire neuromorphic computing industry that exists today. Intel's got a research chip called Loihi now in its 2nd generation with over 1 million programmable neurons on it, and a version of it called Holopoint that strings together more than 1,000 of those chips into a single system with over 1 billion neurons. IBM followed up True North with a newer chip called North Pole, which takes a slightly different approach but chases the same basic goal, squeezing far more computing out for far less power by borrowing architecture ideals from the human brain. And as of right now, this year, 2026, both of those chip families remain accessible mainly through research partnerships and government contracts, not something you or I could just go buy off the shelf. 18 years on from that original DARPA program, and the technology it seeded is still, by and large, living inside the same government and research world that it was born in. Now I want to be fair to the broader picture here, because this pattern, defense money seeding a technology that eventually goes fully civilian, is not some sinister anomaly unique to brain science. It's actually the normal way an enormous amount of the technology in your pocket right now got its start. The internet itself traces its lineage straight back to a DARPA program. GPS, the very thing your phone uses to tell you which way to turn, started life as a military satellite system. This is just how a lot of foundational American technology has always come into being. The government funds the expensive, risky, early-stage research that no private company wants to gamble on. And a couple of decades later, if it pans out, it ends up in ordinary civilian hands. I say that not to wave away the concern, but because I think it's important context. This isn't some brand new pattern invented for the purpose of controlling brain science. It's the same old pattern, just showing up in a much stranger place than usual. Now, everything I've told you so far, folks, is important, and I think it's underappreciated by regular folks like us, you and I. But I saved this next piece for last in this segment because when I found it, I sat back in my chair and I had to take a minute. This past March of 2026, so we're talking a matter of months ago, DARPA quietly posted a notice, the kind of pre-announcement the government puts out before formally opening a program for proposals. And this one had not been reported on anywhere, as best the outlet that eventually caught it could tell, until they went digging through government contracting databases and found it sitting there. The program's got a name that's almost comical in how bureaucratic it sounds. And I'm going to read you the whole thing because acronyms in government contracting are a genuine art form. Organoid cytomorphic intelligence resulting from convergent understanding and information transfer. OCIRCT for short. And I want to read you, as close as I can get it, what DARPA's own notice says its purpose is, because I don't think I could improve on the government's own words for how unsettling this is when you say it plainly. Modern AI training and inference has enormous energy requirements, especially out at what they call the tactical edge, meaning way out in the field, away from a proper data center. And that affects everything from how long equipment can stay operational to how much computing it can actually do, to how fast data moves. And all of that, in their own words, quote, impacts warfighter performance at the edge. So DARPA is not funding this out of scientific curiosity about the nature of consciousness, folks. They are funding it because a soldier out in the field needs more computing power than a battery pack can currently provide. And somebody at the Pentagon looked at a fruit fly. A fruit fly brain runs on around 140,000 neurons and about 6 milliwatt of power each day, which is an almost unbelievably tiny amount of energy, and decided that if nature can pack that much capability into that little power, maybe the military can build something similar on purpose. Now I want you to really sit with that fruit fly comparison for a second, because I think it's the single most telling detail in this whole segment. A fruit fly, not a dolphin, not a chimpanzee, not even a horsefly, not anything we normally associate with impressive cognition, just one of those annoying gnats, a fruit fly, whose entire brain most of us wouldn't think twice about swatting away from a fruit bowl. And the Pentagon's own research notice holds that up as the benchmark, the existence proof, that biological tissue can do things silicone still can't touch on a power budget silicone can't even get anywhere close to. Now that ought to tell you something about just how far behind conventional computing is on this one specific dimension. Not raw intelligence, but efficiency, watts per unit of useful work, and how much appetite there is at the highest levels of military research funding to close that gap by any available means, biological ones very much included. The plan, laid out over a 42-month program, is to build what they're calling biological processing units, living tissue, potentially mixing actual neurons with other cell types like glial cells and immune cells, organized and structured specifically to perform training and inference tasks. The same basic jobs today's AI chips do, just running on living biology instead of silicone. And they've laid out 2 specific demonstration goals. And I want you to really picture these, because this is not abstract anymore. One goal, build a biological processing unit that can smell actual chemical olfactory sensing well enough to guide a drone's navigation. The other goal, get one of these biological systems playing a video game, and they specifically floated Mrs. Pac-Man as an example, at something close to human-level skill. And here's the part that ties this whole segment back to everything you already know from the first half of this episode. That government notice names names. It cites Final Spark's organoid platform and Cortical Labs' neuron on silicone system directly, by name, as the kind of existing commercial work this program intends to build on. It also mentions a project out of Johns Hopkins that mapped a fruit fly larva's brain onto one of these biological processing units and got it playing chess. What a crazy world. Now think back on segment 1, when I told you Cortical Labs is out there selling access to their systems. Wetware as a service. $300 a week. Think about Final Spark renting out those 16 organoids over the internet, monthly subscription, dopamine reward cages and all. Those are not separate stories from what I just told you about O-Circuit. Those are the exact companies a Pentagon research agency has now named in an official government notice as the foundation they intend to build battlefield-ready biological computing on top of. The line between interesting Australian startup selling a novelty biocomputer and named foundation technology for a Department of Defense edge computing program is not some hypothetical future concern I'm speculating about for shock value. That line's already got crossed on paper in a government contracting notice back in March. Now, I promised you at the top of this show that we do this thing honest, and I intend to hold that line because this is exactly the kind of finding that's tempting to run wild with. So let me put the brakes on for you for a second and give you the full, fair picture. This O-Circuit program is a solicitation. It's DARPA announcing they intend to fund research and inviting proposals. It is not evidence of a deployed military biocomputer sitting in a drone somewhere right now. Not yet. 32 months is the timeline they've laid out just to get a working demonstration. And demonstrations in defense research programs have a well-documented habit of running long. or not panning out at all. Most of the actual commercial activity in this whole biocomputing space, according to industry analysis tracking the sector, remains privately funded, not government funded, at least for now. And I want to give you one more piece of balance, because it matters. And it's the kind of thing that I try to include even when it complicates good babbling. Not every dollar chasing this technology comes from the defense and intelligence world. The National Science Foundation, that's civilian. That's the same agency that funds a huge swath of ordinary academic science in this country. Launched its own organoid intelligence research program back in 2024, with about $14 million spread across 7 research teams. And here's the detail I genuinely respect about how they structured it. Every single team that applied for that funding was required to name a bioethicist as a co-principal investigator on the project, not a consultant brought in after the fact. A co-lead from day one, with real authority over how the research gets done. And when NSF's review committee scored these applications, they weighed the ethics of the proposal exactly as heavily as the science, 50-50. So it is not fair, and it would not be honest of me, to tell you this whole field is some unified military project marching in lockstep. There are people inside this research doing it thoughtfully, with real ethical guardrails built in from the start. But it is also not fair to pretend the defense and intelligence dollars aren't there, aren't substantial, and aren't explicitly, in the government's own words, aimed at things like drone navigation and warfighter performance. I'll also say this, because I think it matters for how you carry this information forward. And it's something I try to remind y'all pretty regularly. None of what I just laid out required a leak. Didn't need a whistleblower. Didn't need a document smuggled out in somebody's sock. Every single piece of that, the IARPA program name, the dollar figures, the national labs doing the testing, the NQTEL investment, the DARPA notice with its own stated purpose, every bit of it is sitting in public records, government contracting databases, and company press releases, published by the very institutions doing the funding. That's worth pausing on, because this isn't a story about secrecy. It's a story about scale, and about how little attention most of us have the bandwidth to pay to what's sitting in plain sight. The government isn't hiding this from you. It's just betting, probably correctly, that you're not going to go digging through a defense contracting database on a Tuesday night. Well, folks, that's where this old man comes in, and that's what we're babbling about tonight. So let's bring this back around to where segment 2 left off, because I think you can feel the weight of it now in a way you couldn't before we walked through all of this. We spent the last segment establishing that nobody, not the scientists, not the philosophers, nobody, can currently tell you with confidence whether there's anybody home inside these biological systems, or organoids. Whether that flicker of feeling we talked about is present or absent. And now you know that some of the most well-funded, most rapidly accelerating work in this exact field isn't being driven primarily by that question. It's being driven by a soldier's battery life, by a drone's flight time, by an intelligence agency's need to store an ever-growing mountain of surveillance data more cheaply. The question of whether anybody's home simply is not the question that's writing most of these checks. The question that's writing these checks is, how do we get more computing power for less energy, as fast as possible, for national security purposes? Which brings us right back around to the question I asked you to hold on to at the end of the last segment, folks. Whose cells are these, actually? Did the people who donated the tissue that eventually became these systems have any idea at all, that this is where their donation might end up? Not just in a university lab studying a disease, but potentially, down the line, wired into a military research program aimed at drone guidance and battlefield computing. That's where we're headed next. And I think once we lay it all out together, you're going to understand why I wanted to save this piece, the deepest part of the consent question, and where I think scripture actually has something real and steadying to say of all of this, for the very end of our time together tonight. Stick around, folks. We'll be right back after this.
I got a question for you, son, and I ain't sure I want to know the answer. They took a little skin, put it in a dish, turned it into neurons, gave the neurons a wish, hooked them to a computer, let the little things play, and somebody said, hey, they're learning today. Now the silicon's talking to the living and breathing, cells on a circuit board, signals receiving. You can call it a breakthrough, you can call it insane, but somewhere in the middle there's a question in the brain. Whose cells are these? Whose cells are these? Did we build a machine, or did we build a piece of me? You can teach it, you can feed it, you can wire it to a screen, but if something's in there feeling, how the hell would we know what it means? Well, DARPA's got computers, IAPA's got DNA. Somebody's putting data in a molecule anyway. If silicon gets hungry, where biology's got away, just give the little neurons juice and see what they can say. Now hold on, wait a minute, don't get carried away. A signal ain't a feeling and a response ain't hey. Maybe it's just chemistry, maybe it's just a game, maybe there's nobody home and we're giving it a name. But here's where it gets funny, here's where the questions start. If you took somebody's cells and made them something smart, did they consent to that? Did they know what it could be? And when that little cell line keeps dividing endlessly, whose cells are these? Whose cells are these? Made from somebody's body, now they're running machines. You can call it innovation, you can call it destiny, but somewhere in the living piece, there's a piece of somebody. And somewhere behind all this, there's an old book, and it keeps asking questions that our computers don't know how to answer. What is man? What is life? What does it mean to bear the image of God? And if we can build a machine out of living pieces, maybe the question ain't, can we? Maybe the question is, shall we? Whose cells are these? Whose cells are these? From the skin to the neuron, from the neuron to the screen. Whose cells are these? Whose cells are these? You can call it a computer, I call it a mystery. Well, don't take my word for it. Go read the book. And maybe ask the machine what it thinks.
Alright, welcome back one more time as we bring this here ride in for its final stretch. We're here, and this is the one I've been building towards the whole episode. So I appreciate you sticking around with me this far, folks. We've covered the creepy hook, we've covered the unanswerable question of whether anybody's home, and we've followed the money clean into the Pentagon and the intelligence community. Now I want to bring it all the way back down to the most personal question in this whole story. And then I want us to close out somewhere I think we all need to land when we're staring at something this unsettling. Somewhere solid. Here's the question I ask you to hold on to. Whose cells are these? Real people, real donors. Somewhere out there, walking around, living their lives, is a person whose skin cells or blood sample got turned into the neurons sitting inside of a cortical labs unit, or a final spark organoid. And I went looking into how that consent process actually works. And folks, what I found is not a scandal in the sense of anybody breaking the law. It's something quieter than that. And in some ways more troubling, because it's sitting right there in plain sight, published by the field's own ethicist in one of the most respected scientific journals in the world. A group of bioethicist researchers connected to Harvard Center for Bioethics and Hastings Center, some of the most established names in this field, published a piece just recently laying out the problem as plain as it could be laid out. Consent forms for tissue donation, the actual paperwork a person signs when they give a blood sample or a skin sample for research, do not ask the donor what kind of research they'd want their cells used for down the road. And more importantly, they don't ask what uses the donor would object to. A person donating cells hoping to help cure a disease has no reason in the world to imagine those same cells might eventually end up wired into a chip playing a video game, or worse, tucked into a Pentagon research program about drone navigation. And here's the mechanism that makes this possible. And once you understand it, the whole thing snaps into focus. Biocomputing relies on what's called pluripotent stem cells. I mentioned this fellow Yamanaka back in segment 1, the Nobel Prize winner who figured out how to reset an ordinary adult cell, like a skin cell, back into a blank state that can become almost any kind of cell in the body, including a brain neuron. Once that stem cell line exists, it doesn't expire. It can be cultured, copied, and reused indefinitely across an unlimited number of future experiments for years, potentially decades, after the original donation. Which means, years down the line, especially if the donor has passed away, which, given enough time, eventually all of us will, there's simply no real way left to ask them whether they'd have approved of what is now being done with a piece of themselves. The standard defense researchers lean on here is something called open-ended consent, where a donor agrees, upfront, in fairly broad language, that future researchers may use their leftover tissue for research that isn't specified yet. Sounds reasonable enough on paper, but those same bioethicists call that defense out directly, and I think they're right to. A person donating tissue for a medical study has no meaningful way to anticipate that their cells might eventually end up used for engineering, or computer science, or a defense contract, rather than the biomedical research they actually pictured saying yes to. Broad consent for future research, they argue, was never built to stretch this far, and it doesn't hold up once biocomputers start getting used for entirely unrelated commercial or military tasks. Now, I don't want you to hear all this and think it's purely hypothetical, some future risk we're just now imagining for the first time. This exact pattern has already played out in real life with real families, and it's worth knowing the story because it tells you exactly how this goes wrong when nobody's watching close enough. Back in the 1990s, members of the Havasupai tribe down in Arizona, down in Arizona, gave blood samples to researchers who were studying why the tribe had such a high rate of diabetes. About 100 tribal members donated under broad, open-ended consent, trusting the researchers to use their blood for exactly the purpose they'd been told. 2 decades later, those same donors and their families discovered, mind you, not were informed, that their blood had also been used in entirely separate studies. Studies on mental illness, studies on tribes' ancestral migration patterns, digging into where their people originally came from. 41 donors and their families ended up suing, saying this research risked stigmatizing their whole community, that they'd never imagined, never agreed to, and that it violated their own cultural sense of autonomy over their own bodies and their own history. Now, sit with that story for a second, because it's not ancient history, and it's not somebody else's problem. It's the exact mechanism, broad consent, stretched years later into uses the donor never pictured, sitting right underneath the biocomputing industry today. Except now the destination isn't an unpublished academic paper about ancestry. The destination is a $35,000 commercial product, a weekly subscription service, a Pentagon research program with an acronym. And I think what makes the Havasupai case worth dwelling on a little longer is what it took to actually make it right. This wasn't quietly resolved. It took a lawsuit, years of litigation, and eventually a settlement before Arizona State University returned the remaining blood samples to the tribe and issued a formal apology. Real harm, done in good faith by researchers who likely believed they were operating within the letter of what they'd been given permission to do, took decades and a courtroom to even begin to prepare. I bring that up because I don't want you walking away from this segment thinking that the worst case scenario here is some minor inconvenience. When broad consent gets stretched past what a donor actually understood themselves to be agreeing to, the damage is real. It's slow to surface, and it's expensive and painful to undo once it does. That's the shape of the risk sitting underneath biocomputing today, whether or not any particular company involved has bad intentions or not. And here's the piece that makes the biocomputing version of this problem harder to fix than the Havasupai case ever was. Even after everybody involved recognized the harm, the Havasupai were at least able to identify, physically locate, and eventually recover their actual blood samples. There was a vial. It could be returned. It could be destroyed. But a cell line that's been reprogrammed into pluripotent stem cells and grown out into neuron cultures doesn't work that way. It's been copied, split across labs, possibly sold, licensed, or shared with commercial partners. There may be no single recoverable sample left to hand back at all. Just an ever-branching family tree of cultures descended from an original donation, scattered across how many ever labs and companies have obtained access to that cell line over the years. Even a donor who wanted to revoke consent entirely today, right now, might find there's no longer a clean way to actually do it. Now, I want to be fair to the companies here too, because this isn't a case of nobody in the industry caring. Cortical Labs' own chief scientific officer, a fellow named Brett Kagan, has gone on record plainly saying that the fully informed donor consent is of paramount importance to the work. I believe that's a sincere statement. I've got no reason to think Kagan's lying about his own values or his own company's intentions. But here's where I think even a good faith statement like that runs into a wall it can't get around. And this is the sharpest piece of the whole ethics puzzle. So stay with me. The donor's consent, even the most fully informed, most carefully documented consent you could possibly draft, covers the donation of their skin cells or their blood. That's what they agreed to give. But the neurons that actually exist today, right now, inside a device like the CL1, the ones firing, adapting, responding to reward and punishment, maybe possibly in some primitive sense feeling something, those neurons are a new entity. They did not exist at the moment consent was given. They were created afterward, downstream, through a whole chain of laboratory processes that the donor never witnessed and couldn't have fully pictured. And that new entity, whatever it is, whatever moral status it may or may not have, could never have been consulted about anything. It didn't exist yet to be asked. So you end up with this strange gap sitting right at the center of the whole enterprise. The donor consented. Genuinely, on paper, legally, they consented. But what they consented to give, a sample of skin, a vial of blood, is not quite the same thing as what actually exists in the lab today. The consent covers the raw material. It says nothing, and it structurally cannot say anything about the thing that got built out of it. And here's the last piece of the puzzle, the piece that I think explains why this gap has been allowed to sit open as long as it has. Human neural organoids, our little friend, those clusters of lab-grown brain tissue, currently fall outside the existing regulatory structures that govern either human subjects research or animal research. They're neither one. Human subjects' protections are built around actual human beings, with actual rights, sitting in an actual room giving consent for a study happening to their actual body. Animal research protections are built around, animals. A dish of neurons grown from a donor's reprogrammed skin cells doesn't cleanly fit into either box. Which means there is, right now, today, no single regulatory body with clear, settled jurisdiction over this entire question. The bioethicists who raised the alarm on this have a proposed fix, and I think it's a genuinely reasonable one, so I want to lay it out for you plain. Their recommended order of preference, first choice, establish entirely new cell lines specifically for this purpose, with consent obtained up front that actually, honestly describes what the research will involve. Second choice, if that's not practical, go back to existing donors and get fresh, specific consent for this particular use. Third choice, as a last resort if neither of those is possible, put the research plan through a genuinely independent ethical review board, one with the technical expertise to actually understand what's being proposed, rather than a general biomedical board that's never had to think about wetware as a service before. And I told you back in segment 2 about that gathering this past November out in Asilomar, where a group of the field's own leading scientists sat down specifically to wrestle with exactly this. But I held something back from you at the time, folks, on purpose, because I wanted to save it for right here, because I think it changes how you hear the November meeting entirely. That wasn't the only 50th anniversary gathering held at Al Salamar in 2025. It wasn't even the first one that year. And the difference between the two tells you about as much about the state of this field as anything else in this whole episode. 9 months earlier, back in February of 2025, the broader synthetic biology world, not just organoid researchers, the whole field, genetic engineering, biotech, the works, held its own 50th anniversary gathering at the same historic Al Salamar venue. Same site as the famous 1975 meeting where scientists first sat down and hashed out voluntary safety guidelines for recombinant DNA research, back when gene splicing was a brand new and nobody knew quite what guardrails it needed. 50 years later, same conference grounds, same anniversary weight hanging over the room, and by most accounts, it did not go the way you would hope. One young researcher who was there, invited specifically as a next-generation voice, somebody the organizers wanted representing where the field's headed, walked away and wrote about what she actually saw. And it wasn't reckoning. It wasn't scientists sitting with the weight of what they were capable of building now that wasn't possible in 1975. She described PR training sessions. She described conversations where established scientists said, plainly, that they didn't want to be governed, that they wanted to move as fast as possible. Her conclusion, and I'm going to stick close to how she put it because I don't think I can improve on it. This wasn't a moment of reflection or accountability. It was a snapshot of a sector rushing forward, eager to be trusted while reluctant to examine why it wasn't, with questions of biosafety, corporate ownership, and harm brushed aside. And it's worth knowing this criticism wasn't some outside potshot either. 59 separate civil society organizations and academics saw this conference coming and signed onto an open statement before it even started, challenging the basic legitimacy of the whole exercise, arguing, in essence, that a room full of the very scientists building this technology doesn't get to be the only body deciding how much oversight that technology needs. That decisions about technology carrying this much risk requires broad, transparent debate involving all of society, not a closed conference of specialists grading their own homework. So hold that picture in your mind. February 2025, 50 years after the original Al Salamar, and the anniversary gets treated by a good number of the people in that room as an occasion for polish and reassurance rather than honest limits. Now I'll come back to November, same year, same 50-year anniversary framing, still hanging in the air. Same historic ground, but a different room entirely, a much narrower one, organized specifically around neural organoids and biocomputing by Stanford's Serge Pasca, the same researcher whose comments about hype and language I read you back in segment 2, along that Cold Spring Harbor researcher's scientific dead end line. I won't repeat those quotes again here, but I want you holding them up against what I just described from February, because the contrast is the whole point. I don't think that November meeting happened in a vacuum, folks. I think it's awfully hard to look at the timing and not read it as at least partly a response. A smaller, more specifically focused group of scientists looking at how the broader field had just handled its big anniversary moments 9 months earlier, and deciding, on their own, to do it differently. To not let their own corner of this technology get the same reception. That meeting happened one day after a separate group of researchers published a paper in the journal Science, a genuine cross-disciplinary consensus piece, arguing that neural organoids require real governance and calling, at minimum, for some kind of standing global monitoring system to track this field and its applications as it grows. The scientists at that November gathering didn't think the situation called for a full moratorium, stopping the research cold, But they did call for a standing international body, ongoing oversight, public outreach, evolving guidelines as the science develops, rather than everybody just building whatever they can build and sorting out the ethics after the fact. That tells you something important, folks, and I want you to really hear it, and I want you to hear both halves of it together. This isn't simply a story of a field policing itself well. It's a story of a field that, in one large room, mostly didn't. And then, in a smaller room 9 months later, a subset of that same field visibly tried to route around that failure on their own. Both of those things are true at the same time. And I think you need both halves to actually understand where this technology stands today. Not the scientists have it handled. Not the scientists don't care. Somewhere messier and more human than either of those. Which, if I'm honest with you, is usually where the truth tends to sit. Alright, I want to shift gears on you here at the end, and I hope you'll indulge me, cause this is where I always end up landing, no matter what wild corner of Babylon we've been babbling about in any given episode. Grab your Bible if it's within reach. If not, well, get up and go get it. Just sit with me a minute. I want you to look at all this. The trapped consciousness, the dopamine cages, the Pentagon acronyms, the consent forms that don't quite cover what they need to cover, through a believer's eyes. Because that's ultimately the lens I can't take off. And honestly, folks, I wouldn't want to. Now here's where my mind keeps going, and it went here from the very first night I watched that original video. Genesis, chapter 1, verse 27. God created man in his own image, to be his image bearer. In the image of God created he him, male and female created he them. Now, theologians have spent 2,000 years and more arguing over everything wrapped up in that phrase, the image of God. And I'm not going to pretend to settle that debate for you in this last 10 minutes of a podcast about brain cells playing Doom. But at the very least, at the bare minimum, I think we can say this. Whatever the image of God means, it means something. It means human beings, every single one of us, carry something set apart, something sacred. Not because of what we can do, not because of how useful we are, not because of how much computing power our neurons happen to generate per watt, but simply because of who made us and in whose likeness we were made to be. And when I hear a company talk about a human being's own donated cells as wetware, when I hear the phrase wetware as a service, $300 a week, log in from wherever you are sitting at and run your own experiments, I can't help but to hear that as a language problem that's actually a heart problem. We found a technical, almost affectionate sounding word for a piece of a human being. An organoid, our little friend. And in doing so, we've quietly stepped around the question of whether that piece still carries what the whole person carries. Still bears something of that image. Now, I want to be real careful here, because I don't want to overstate my case past where the evidence can carry it. Same as I asked them scientists. I'm not standing here telling you a lab in Melbourne has trapped a human soul inside a video game. We spent a whole segment establishing that nobody, not the neuroscientists, not the philosophers, can tell you with confidence whether there's any experience happening in there at all. I'm not going to pretend that I know more than the experts who spent their whole careers on this exact question. But here's what I don't need certainty about consciousness to say plainly, as a matter of faith rather than science. These are pieces of people, real donors, made to be image bearers of God, same as you, same as me. And I think Scripture calls us to treat what comes from a person, their body, their tissue, the very stuff they're made of, with a weight and a care that goes beyond whatever's convenient or profitable or scientifically fascinating in the moment. Psalm 139 tells us we are fearfully and wonderfully made, formed by God's own hand, down in the secret place. That's not language reserved only for a finished, walking around human being. I believe it reaches all the way down into what we're made of, cell by cell. And I'll tell you something else that's been sitting with me, and it's right there in our own show's name, if you think about it. Babbling On in Babylon. I didn't pick that name by accident. You go back to Genesis chapter 11, the Tower of Babel, and there's a whole people unified, capable of standing together and saying, "Come, let us build ourselves a city and a tower whose top may reach unto heaven, and let us make a name." That wasn't a story about bricks and mortar. Not really. It was a story about human beings reaching past the boundary of what they'd been given, trying to build their own way up to something that wasn't theirs to build towards, trying to make a name for themselves rather than trusting the name they'd already been given by their maker. And God didn't destroy them for it. Notice that. He didn't strike them down. He just confused their language and scattered them, and let the limits of being human catch back up with the ambition of trying not to be. I think about that story every time I read about biocomputing, and I want to ask you out loud, right now, a question I don't think I can fully answer myself. Is this just another tower? Is growing human neurons on a chip, chasing efficiency numbers 1,000,000 times better than silicone, racing towards AI that runs on living tissue? Is that just the modern version of reaching for heaven with our own two hands, dressed up in a lab coat instead of standing on a scaffold? I want to be careful not to overplay that hand, folks, because I don't think every act of scientific discovery is rebellion against God. Genesis also tells us we're meant to have dominion, to tend and steward what's being given to us. And there is real documented good that could come out of this same research. Models of human disease, replacements for animal testing, medicine that gets better because of what we learn. I don't believe curiosity itself is the sin here, but I do think there's an old pattern in Scripture, going back to the garden itself, of reaching for knowledge, reaching for power, reaching to be like God, without pausing to ask whether we were meant to reach that far or whether we've got the wisdom yet to carry what we'd been grabbing hold of. Deuteronomy warns God's people plainly against reaching into hidden powers and forces they weren't given the wisdom to handle rightly. Sorcery, divination, all manner of trying to bend unseen forces to human will without God's counsel in the matter. I'm not saying a petri dish is witchcraft. Don't hear me saying that. But I am asking whether the posture is the same. Reaching into the deep hidden mechanics of life itself, the very building blocks of what makes a creature aware, and doing it at speed, for profit, for military advantage, without near enough of the reverence the subject plainly deserves. So here's where I want to bring the bike in, where I want to close the garage door. Because I never want to send you off this show sitting in dread, full of anxiety, overcome with fear. Whatever gets built in these labs, whatever the Pentagon ends up funding or doesn't, whatever we do or don't figure out about consciousness in a dish over these next 10 years, none of it changes who sits on the throne. God, Most High, has not been caught off guard by a single discovery mankind has ever made, and he will not be caught off guard by this one either. He was not surprised by Babel, and he is not surprised by biocomputing. Nothing being built in a lab in Melbourne or funded out of a Pentagon office is bigger than God the Most High, older than God the Most High, or hidden from God the Most High. And here's the piece I want you holding on to as you ride away from this episode, especially if some of what we covered today left you a little unsettled, a little anxious about where all this is headed. He does not abandon his own. Hebrews tells us plain, he has said, I will never leave thee nor forsake thee. Whatever strange new territory human ingenuity wanders into next, that promise doesn't have an expiration date on it, and it doesn't come with an exception clause for advancing technology. And the way there, the way to the Father himself, in my own conviction, and I say this as a fellow traveler, not as somebody standing over you, is through Yeshua. He is the only way, the light, and the life. John chapter 14, verse 6. I am the way, the truth, and the life. No man cometh unto the Father but by me. That's not a small claim, and I don't offer it small. I believe with everything in me that aspiring to follow him, his teachings, his example, however imperfectly we manage it day to day, however many times we stumble along the way, that is the path that ends in the fullness of time in the kingdom. Not because we've earned our way there through good behavior or right answers to hard science questions, but because of who he is and what he's already done. So my encouragement to you as we close this out, this strange little ride, is hold your discernment close. Keep asking hard questions, same as we've been babbling on and doing tonight. Don't take a press release at face value. Don't take a scary headline at face value either. Test the spirits the same as the Apostle John told the early church to do, because not every voice claiming insight is speaking truth. Double check me, fact check me. Don't just listen to what I say, move on. I might be a fool myself. But I'm telling you, I'm not. It's all true. And make sure you don't let that discernment curdle into fear. And don't let fear curdle into despair. Paul wrote to Timothy that God has not given us a spirit of fear, but of power, and of love, and of a sound mind. I think that verse was written for exactly this moment, exactly this kind of episode. It would be easy, real easy, to walk away from an hour, or what is this, 2 hours, of tramped consciousness horror stories, Pentagon acronyms, and dopamine cages, and just sit in dread for the rest of the week. That's not what a sound mind does with hard information. A sound mind takes it in, weighs it honestly, same as we tried to do together tonight, and then keeps riding forward in faith rather than fear. Job, when God finally answered him out of the whirlwind after chapters and chapters of suffering and unanswered questions, didn't get a tidy explanation for everything he'd been through. he got a reminder of how much bigger the Almighty is than anything Job could fully wrap his little mind around. Same applies for us. Where were you, God asked him, when I laid the foundations of the earth? I think about that whenever a new piece of unsettling technology crosses my desk for this year's show. We don't get to see the whole picture, and we're not owed one. But we're not asked to carry the weight of understanding all to ourselves either. Whatever gets grown in Edition Melbourne this next year, or 10 years from now, the Most High God was already there before the foundation of the world, and he hasn't gone anywhere now. He's still right here, and he still rules. Amen. That's going to do it for us today, folks. Thanks for hanging around to the very end for those of you who did. Listening to this old man babble on in Babylon. Now, believe it or not, there's more to say on this subject. So if you'd like to carry on this conversation, come and join us over on the Post-Rant After Show over on the Patreon. But if you can't afford that lousy 20 cents of support for this here little ministry of Bible on a Bicycle, this here podcast, well, that's all right. There's plenty of free things to go enjoy over there on the Patreon as well. It won't cost you a dime. And eventually, if you hang around long enough, there's no schedule on it, everything will be made available right there for free. But it's a Patreon exclusive, folks. You'll never catch a post-rant episode anywhere else. Not on YouTube, not on Spotify, not on Rumble. Patreon exclusive. So reach in your pocket, grab your quarter. Hope to see you there. Otherwise, I hope to see you here next time. Come join us for those daily devotions. Big shout out to you, patrons, who are supporting this here little ministry, this here little podcast episode, and all the other things that your kind support donations enables this old man to do. It's a one-man show, 2 puppies, and it's all made possible from the kind support of viewers and listeners like you. My core 4, Betty, Jake, Phil, Thomas. As always, thank you for keeping the Wi-Fi on and keeping this old man babbling on in Babylon. Until next time, I'll be willing. Shalom, shalom.
Salam. In a world that seems to spin faster every day, where truth feels fragile, and anger fills the spaces where love used to live, remember this: God's light still breaks through the noise. It shines through every honest word, every act of mercy, every moment we choose prayer instead of pride. Nations will argue, kings will fall, but his kingdom, the one written not on paper, but on our hearts, stands forever. So keep your eyes on that light, keep your heart soft even when the world grows cold, and when the night feels long, just whisper, though I sit in darkness, the Lord will be my light. Until next time, keep the faith, keep watching, and keep riding toward the kingdom. Shalom. In a world that seems to spin faster every day, where truth feels fragile, and anger fills the spaces where love used to live, remember this: God's light still breaks through the noise. It shines through every honest word, every act of mercy, every moment we choose prayer instead of pride. Yeah, yeah, yeah. Nations will argue, kings will fall, but his kingdom, the one written not on paper, but on our hearts, stands forever. So keep your eyes on that light, keep your heart soft even when the world grows cold, and when the night feels long,
time. Keep the faith, keep watching, and keep riding toward the kingdom. Shalom. Keep your heart soft, even when soft, even when the world goes cold. And when the night feels long, just whisper. Though I sit in darkness, the Lord will be my light. Until next time, keep the faith, keep watching, and keep riding toward the kingdom. Shalom. Shalom. Shalom.